Hello again, YouTube. The last time we looked at Modbus protocol over RS485, which is a master-slave protocol, and I looked at it with somebody else's implementation of a master and a slave. This is time we're moving on to CAN bus, which is pretty much what the cinnamonBun was designed as. It's more or less designed as a development platform for CAN bus. And this is my little test bus with 4 nodes, or positions for 4 nodes. The orange and white and orange are the power and ground, and then the blue pair are my CAN bus, which is terminated on both sides just with a very simple 120 ohm resistor for termination purposes. So the CAN bus, Modbus was a master-slave protocol, and CAN bus is a multi-master or peer-to-peer network where anybody can transmit at any time. Just to go through these connections on the cinnamonBun, the center is power and the 2 outside are ground. So if you reverse the connection, power and ground are still in the same position. The CAN high and CAN low are on the outside. There's another 3-pin connector I haven't soldered in here, which is CAN high, CAN low and ground. In the RS485 physical layer, the differential signal is marked A and B. So the twisted pair are A and B. In CAN bus, they're referred to as high and low. Now, if I connect up my node here, I have to consistently connect. So if I'm connecting CAN high to the solid blue, then all nodes have to connect the same orientation. Otherwise we're going to have problems on the bus. So CAN high, CAN low, differential pair. When we talked about Modbus transmitted an address byte. The first byte that's transmitted is an address byte, followed by the command that you want. So we looked at reading registers and reading coils as an example. And the Modbus is a master-slave protocol, so only the master can communicate when it's in the idle state, and it can ask a specific master for a response. So it's a command response protocol. So the master says, we used it to read a temperature from a device. So what's the temperature and humidity? Read that those registers back, and then sit and wait, and then later, a second later or whatever, we poll again and say what's the temperature. In the CAN bus, any node on any of these connections, they're peer-to-peer. Anybody can talk or transmit. As a result, the protocol is quite complicated. It's got a lot of intricacies. It uses collision detection. There's a priority on the frames, and that is all handled in the silicon, in this case of the DSPIC33. And if 2 nodes transmit at the same time, one will back off. The other will transmit, and then the one that backed off will wait for a quiet period on the transmission medium, and then it will try again to transmit. This is all shielded from you by an API in the lib-soup development. So if we look at some code in the lib-soup directory, in examples, there's a file there, CAN main, and it's CAN bare bones. So it's a main for CAN bare bones, and there's a project in a microchip project in projects. There is a CAN bare bones project down there. So if we look at this example very quickly, now I'm not going to get into too much details. I just want to do a very stripped down, bare bones look at CAN bus protocol. And I'm going to use, previously I did a hello world in the very first videos on embedded systems and using this cinnamonBun, and I used this little daughter board, which is a LED on pin D0, a LED on pin D1, and then a switch on pin D2, and I replicated the same pattern on both. So as I said, Modbus is address and command. CAN bus does not have addresses. Now, even though I talk about CAN at layer 2, so CAN bus layer 2 transmit a frame, the OSI 7 layer model, which I discussed briefly, layer 2 of that standard specifies that a frame contains a source and a destination address. CAN bus has no addressing at layer 2. A CAN bus has an identifier which is it was a standard from the 1980s, and the original standard had an 11-bit identifier, so from 0 up to 3FF, 11 bits. It also carries a payload of up to 8 data bytes. In this case, we're setting that to the DCL to 0, so we're not transmitting any data bytes on this frame. And then the API hides out all the details from us, and it just calls transmit. So we're just saying transmit this frame. An identifier of 777, and that's a standard frame identifier. If we go down in the code here, we'll go through this. These are 2 callbacks. We'll come to them, and that the change and the frame handler. So first thing we do is we initialize libEsoup as usual. We've added CAN bus into the mix, and we've said we want the code to be able to handle 10 frame handlers. The other 2 we'll talk about in future videos. I'll strip this right back to the basics. So initialize the libEsoup, and we want to set pin D0 as an output, initialize it to 0. Pin D1 as an output, initialize it to 0. And pin D2 is our input. As well as initializing it, we set up this change notifier. So the libEsoup API, the code underneath is going to monitor that pin, or D2. If it changes, we're going to call this callback. So this is an asynchronous callback, an event handler, if you will, on a change on pin RD2. So that's our I/O pin setup. We initialize the CAN bus. Now we're initializing a baud rate. So we'll take 250k. CAN bus is specified up to 1 megabits per second for, I think it's a 30-meter bus length. It was designed originally by Bosch for the automotive industry, so if you've got a 30-meter twisted pair going around a car, that's more than enough. 30 meters is more than enough for that environment. Now you can slow it down if you extend the bus length, then you can slow down the baud rate, but we'll keep it at 250k. Like I say, it goes up to 1 megabit, and given the length of cable I have here, I should be more than able to do 1 megabit. So second parameter is callback, which we'll get to later. For the moment we'll leave it null, and the third parameter is the mode of CAN bus mode of operation we want to power up in. Normal is just, as the name suggests, normal. There are loop back into modes, there are listen only modes, but for the minute we want a normal mode where we acknowledge and we interact with the bus, we transmit and we receive messages on the bus, frames on the bus. Because this is layer 2, layer 2 protocols transmit and receive frames. I sometimes slip and say messages, but at layer 2 level it's a frame. So we've initialized the bus, and the next thing we want to do is set up a frame handler. This is a frame that we are interested in processing. So in the CAN bus specification, you talk about filter and mask. So this is the value that we're interested in, the CAN bus identifier that we're interested in. Now, we've set up a mask. The mask is any bit that's set in the mask. We are interested in that bit value. If it's a 0, if the mask bit is 0 at a position, we don't care. So in the case of this, that SFF mask is the standard frame mask, which is 11 bits. So it's 3FF. Sorry, 3 bits is 7FF. So because we've set all those bits of the mask, we're interested in all 11 bits of the identifier. So we'll only expressing an interest in the value 777. If I set a mask of 7F0, then I'm only interested in 77, and I don't care what the last nibble is. So that's expressing an interest in a block of 16 CAN bus identifiers from 770 up to 77F. But we are actually, in this case, I only want to receive one frame. I'm only interested in one frame, 777. The other flag is in the code, the CAN bus identifier is stored in a 32-bit value. And the highest bit of that the standard frame is 11 bits, the extended is 29 bits. In the identifier, the way the identifier is stored in code, the highest bit, so the highest bit, the most significant bit, indicates that it's if that's set, it indicates that it's an extended frame. So in this case, that mask bit is set, so I'm interested in matching that bit. And because that 32-bit value is, if you like, the highest bit is 0, I'm only interested in standard frame. So this, we're registering a frame handler for a standard frame of value of identifier, 11-bit identifier 777, and we're telling the API we're interested in that handler or in that frame, and anytime we receive that frame, we want this frame handler to be called, and then we just enter our main loop and do the libby soup tasks. And these two, the frame handler and the change notification handler, these two callbacks will be called asynchronously. So they're like event handlers. Whenever something changes, whenever a frame is received, whenever the pin changes, those functions will be called. So that code is running in both these nodes. So these CAN bus nodes are both basically sitting waiting for a change on pin 2. So if I press this button, I'm going to transmit a 777 frame, a standard 777 frame, and when I release it, there's another change, I'm going to send another 777 frame. Now when this node transmits a 777, you'll notice he doesn't light his LED. He does not receive what he transmits. So he only receives if he transmits. If this node transmits, this node will receive it. If this node transmits, this node will receive it. If anybody else transmits, they'll both receive it. You don't receive what you transmit yourself. That would be loopback mode, and that's only used for test. So this node is a very simple node, no expansion, but I've got a timer, a 1-second timer, and all this node does is send out a 777 frame. So in this case, he's sending out 777 and both nodes are reacting. Now if I press the button on this node, he will send out a 777, so this device or this node will get an extra 777 frame and the LEDs will go out of sync. If I release it, then he'll get another extra 777, but he'll go back into sync because it's only on and off, and that's our CAN bus. Very simple an identifier. Now if you get into the extended and the 11-bit standard and the 29-bit extended identifier, I'm sending out 777. When the pin changes, I'm just sending out this frame 777. A standard a standard 11-bit identifier 777 with 0 data bytes as payload, and transmit that frame. The frame handler, when a node receives a 77 frame, just toggles RD0. So that's a very simple. When you receive this frame, just toggle that bit. Now if I take this flag, which is the extended, when I do a change on a pin, I'm sending a 777 standard frame as it was. If I now set this flag, I'm now sending a 777 extended flag. So this is like the difference between the standard 11-bit identifier and the 29-bit identifier. It's not exactly the same, but it's like if you had a 16-bit value in a computer or a C program and a 32-bit identifier or a 32-bit value, both can be 777, but they're two different lengths. This time I'm sending out, if there's a change on the pin, I'm going to send out an extended 777. So this is a 29-bit identifier, and I'm just going to program this into the first. So now, previously when I pressed this button, they went out of sync. But if I now press this button, it's going to have no effect, because I'm sending out a 29-bit identifier. If you look at the code, our handler is saying we are only interested in 777, and we're interested in, the mask is set to say we're interested in what the flag is. So we're only interested in this case, we're only interested in standard 11-bit. If I change this to be, if I get rid of that, so now the top bit of the mask is not set. That means I don't care whether this is a standard 11-bit identifier or a 29-bit identifier. I'm only interested in the value 777. So whether it's a standard or extended 777, I want to handle that, and this is my frame handler for doing that. So if I program that into the second node, so as it is, the second node is ignoring the first node sending an extended frame. But if I program up this version, now the second node won't care whether it's a standard or an extended. So now if I press this, we're now out of sync again, because the second node is processing both a standard length 777 and an extended length 777. So that's my introduction to CAN bus. There are no addresses. Anybody, any node on the network can transmit at any time. The silicon implements collision detection. The priority is on the lower. If two nodes transmit at the same time, the node with the lower numerical value of a CAN bus identifier wins, is the highest priority. So the lower the number, the lower the identifier, the higher the priority. So the one with the highest value will back off, wait for a break in transmission, and then it will transmit his frame. That's it. It's because an API can hide all the details. There's more to it than this. There's retries. There's information requests. There's all sorts of stuff. But basically, you're sending an identifier with 8 bytes of data over a twisted pair differential signal, and I can show you that on a scope sometime. But that it's very similar to RS485. And I leave it there. That the code is up on GitHub in libsoup. If you have any questions, ask them. I hope this is useful. This is a lot of people who know the ins and outs of CAN bus will say this is a very, I'm missing out a lot of stuff, and I am. But this is a very basic introduction into the way the protocol works. We can get into the details, the finer points of it later. I hope that's of use to somebody, and hopefully now that I've got to CAN bus, we can actually progress and make some more regular videos, because CAN bus was what this was all, the cinnamonBun was all about. Thanks a million for watching, and I'll talk to you again soon.